Hi, I'm James. This is a DFA to represent the snake game. Snake game is a game where a snake moves across a board and tries to collect apples. The game is over when the snake runs into itself or a wall. We construct the finite automaton as a DFA, which we represent as a five-tuple, with a set of states, a set of inputs, a transition function, a start state, and a set of accept states. The input alphabet accepts 5 characters. It accepts up, right, down, left. It also accepts a null symbol, which indicates that the user didn't input any new direction for that game tick, and the snake continues along its current trajectory. The snake game keeps track of several variables, including the position of the snake's head, the direction that the snake is going, the position of the apple, everything about all of the pixels in the snake's body, and the score, along with some other things. To represent the snake game as a whole as a finite automaton, we'll first construct some smaller finite automatons to represent each of these variables. The points variable can be constructed out of a finite automaton with 1008 states, and that finite automaton basically looks like a list where each state can travel to the next state if the snake eats an apple, or transitions back to itself if the snake does not eat an apple. The direction is represented with 4 states: up, right, down, and left. There's a state which I call incoming tail, which represents the number of pixels that the snake has to grow by after eating an apple. So right now the snake won't grow at all, so it has an incoming tail of 0. But after it eats the apple, it will grow by 5. So right now it has an incoming tail of 4, 3, 2, 1, and now 0. The snake game stores a Boolean variable called second chance that gives the snake 1 extra game tick to try to save itself after it hits itself or a wall. Because this is a Boolean, this is represented with 2 states, where second chance is on if a collision occurs, or off otherwise. The snake's head position can be thought of as a 2-dimensional matrix, the same width and height as the board. The snake's head can move up, right, down, or left. The apple position can also be thought of as a 2-dimensional matrix. However, the transition arrows are a bit more like spaghetti here. That's because when the apple is eaten, then it moves to a new random spot on the board. The spot the apple moves to is generated using the pseudo-random algorithm, which basically takes a hash of the snake's state, modulo the number of open spaces on the board. The snake's body can be thought of as a queue of directions, which can be traced back from the head to the end of its tail. Because there are 4 directions, each direction can be enumerated to a specific number between 0 and 3. Then this list of directions can be thought of as a base 4 number. Because the size of this number matters, and a number with leading zeros represents a different state than a number with no leading zeros, the number of states represented by the snake's body is a sum of the possible base 4 numbers between 0 and the snake's maximum body size of 1007. Now we can combine all of these parts to get the actual finite automaton state. The set of states is the Cartesian product of the set of point states, the set of direction states, the incoming tail states, chance states, apple states, head states, body states, and there's also a accept state and a reject state. This leads to 1.656 times 10 to the 619 states. For reference, the number of atoms in the known universe is estimated to be about 10 to the 82, and the number of unique chess matches is 10 to the 120. We can enumerate these states so that there is a unique subscript I for every state in Q between 0 and 1.656 times 10 to the 619. Conversely, we can use this subscript to figure out exactly what state the game is in. Finally, we can define our transition function, which is the small text on the right. For example, this is the subscript of the start state, and this is the subscript that we get from the transition function with an up input. The website gives a more detailed construction of the finite automaton. It also has a visualization, which lets you play the snake game and see the current states and previous transitions.